Let's move to the second talk of the day on deep learning methods for audio-EEG analysis by Jaswanth, Reddy, Katthi. He's an MTech research student in W department under the program System Science and Signal Processing, and has recently presented his thesis colloquium talk. Being a part of Lead Lab, he pursued his research under the guidance of Dr. Sriram Ganapathy. Currently, he is a camera systems engineer at Qualcomm Hyderabad's Multimedia Systems Division. His research interests involve machine learning, signal processing, and cognitive neuroscience. Welcome, Jaswanth, and the floor is all yours.
Yeah, thank you, RK. Okay, let me share my screen. Okay, 1 second. Okay, is it visible? Okay.
Yes, it is.
Yes, sure. Okay. Thank you. I would like to thank IEEE-IISc Communication Society chapter for giving me this opportunity, and everyone who is responsible, who is a reason for me to speak here. Yeah. So, hi everyone. I'm Jaswanth, and today we are going to discuss about my work with Dr. Sriram Ganapathy on deep learning methods for audio EEG analysis. So the motivation to this work is quite easy. We do a lot of works in our day-to-day life. Everything we do and everything we are, we owe it to our brains. So brains help us to move on two legs, to hunt for food, to discover fire and cook our food, to start agriculture, to start building villages, towns, civilizations, to enhance our warfare, and other artistic pursuits like music, art, and cognitive activities like driving. And all of this are possible because of our brains. Our brains perform multiple voluntary and involuntary actions and process all the information pouring in at it through different modes simultaneously. All the sensory information it gets, it processes that and aggregates their output and estimate the environment around us. But very little is known about how our brain processes information. Multiple paradigms evolved to understand this. Signal processing approach tries to look at brain as a system that takes an input, processes it, and produces an output. A system level approach tries to divide brain into some systems and understand them individually and relation among them. Neuronal level and molecular level approaches go close to neuron or neurotransmitters, respectively, and see how they interact and how they are responsible for how our brains work. Auditory neuroscience is a branch of neuroscience that deals with the perception and processing of acoustic information inside our brains. Our brain is very energy efficient. It doesn't require much power. It doesn't get heat up so easily. It's robust in processing. We don't need to perform critical math to do our daily things. And it is not data hungry. We learn quite easily. We don't need a lot of data to learn something, which are the major requirements of today's data-driven machine learning models. Our auditory systems are also very efficient in our daily tasks, like they are not error-prone to reverberation effects. We can focus on a particular sound or a particular speaker among multiple sound sources, or we can even enjoy the harmony of multiple sound sources as music. These properties of our auditory systems attract more research into decoding them. Understanding the auditory systems helps us to improve the existing artificial systems and alleviate the impairment problems among humans. So basically, the broad goal is to understand how brains process auditory information and how it is linked to other systems. To understand this, generally what we can do is we can provide a stimulus to the brain, collect its corresponding response, and try to model the relationship between the stimulus and the response. So today's talk, we are going to discuss about recent machine learning techniques which have been deployed to model this relationship between the stimulus and response for a naturalistic auditory stimulus and its corresponding brain response. Now, how to represent the stimulus and the brain response? An auditory signal consists of abundant amount of information. Like it consists of the speaker, what is the accent of the speaker, what is the language the conversation is going on, what is the ambience, the context of the particular audio, the emotion being present, and the vocabulary being used. And if it is a music, then it also consists of the information like instruments being used in the song or what is the genre of the song. So how are we going to represent such a complicated auditory stimulus? For stimulus response correlation analysis kind of experiments, generally we use two kinds of representations. One is the envelope of the auditory stimulus, and the other is the spectrogram, which provides time and frequency analysis kind of representation to see which frequencies are present at which instant of time in a particular auditory stimulus. And now, how can we represent the brain? How can we collect the brain response? There are multiple techniques like electroencephalography, magnetoencephalography, electrocorticography, and functional MRI. Each of them have their own set of advantages and disadvantages. Like EEG, MEG, and fMRI are non-invasive techniques, where the first two, that is EEG and MEG, provide better temporal resolution, and fMRI provides better spatial resolution. And a lot of experiments for stimulus response correlation analysis for auditory stimulus is being done on EEG, because EEG is very inexpensive, it is portable, it is non-invasive, that is, we need not open a scalp to record the brain signals. It is relatively easy to record, and it offers appreciable temporal resolution, which allows us to capture processes going inside our brain more precisely. fMRI provides better spatial resolution, which can help us to understand where a response is being evoked from, but it provides very less temporal resolution. ECOG, on the other hand, can provides both temporal resolution and spatial resolution, but it is an invasive technique which limits its use. Therefore, we can understand why EEG is preferred to capture brain responses for understanding auditory perception. But as EEG records brain signals from the scalp, it can record other processes which is being performed by brain, like maintaining the subject systems. They also get captured. Therefore, EEG recordings capture the processes that are not at all related to the stimulus along with the desired response. Also, some stimuli induce responses which are evoked in the middle of the brain might get smeared out while propagating out to the scalp. Hence, EEG recordings contain significant amount of signals that are not related to the stimuli presented to the subject and does not contain all the responses which were evoked by the stimuli. All these signals can be considered as noise, and EEG recordings are very noisy in this view, with SNR being less than minus 20 dB. So this significant amount of noise in each recording makes it difficult to analyze the stimulus-response relationship. Therefore, the initial studies focused on short-term stimuli, which existed less than 2 seconds, and event-related potential methods. The ERP methods, they alleviate this problem of noise by repeating an experiment multiple times and aggregating the responses. This helps us to remove the brain responses or EEG recordings which are not related to the presented stimuli. But this cannot be extended to longer naturalistic stimuli, because we cannot repeat it or at the same time for multiple subjects. To analyze our stimulus response relationship for longer naturalistic stimuli, we we need efficient single trial analysis techniques. So that brings us to the background for single trial analysis techniques. The most successful and prevalent single trial decoding techniques exist assume a linear and time invariant impulse response between the stimulus and the brain response. And temporal response function, TRF, earliest method in this direction, uh, is majorly used in two modes. One is encoder mode, that is also called as a forward model, where we try to predict the EEG response from the presented audio. Whereas the backward model, which are also called as decoders, they try to predict the features of the stimulus from the EEG responses recorded. To visualize it properly, so let's say we have an audio stimulus which is pre-processed and represented as S, which was presented to brain, and the corresponding EEG responses are represented as R. Now we need to perform the stimulus response relationship between S and R. The encoder model tries to transform stimulus S using a function f such that this new representation is closer to the response R. Whereas for decoder model, we try to transform response to make it closer to S. In hybrid models, both the signals are transformed such that the final representations are closer to each other. And this closeness is quantified using Pearson correlation coefficient between the true signal, which is trying to be estimated, and the predicted signal. And as we have discussed that these models are linear, we can replace this function by a matrix. So here we can replace the function f by a matrix capital F and function g by a matrix capital G. And here we need to find out these matrices. And these are found out in the existing prevalent techniques using ridge regression. We know that EEG is very noisy, and therefore only a fraction of the variance on either side of the signal can be explained by the other signal, which results in Pearson correlation coefficients very small values, that is between 0.1 and 0.2. Canonical correlation analysis, CCA, is a hybrid model which is prominently used in this naturalistic auditory stimulus setting. Here, the stimulus and the responses are transformed onto a common subspace using linear transforms. Therefore, we can represent them using two matrices. So here, the stimulus x is transformed onto a common subspace as x dash using u, and y is a response. Y is the brain response corresponding to the stimulus x, and it is transformed onto a common subspace using the matrix v. And the optimum transforms, that is u and v, are obtained by maximizing the correlation between the final representations. So here, if u1 and v1 are the transforms, and cxx, cxy, and cyy are the correlation matrices, then we try to find the optimum transforms by maximizing the correlation between the obtained representations. And this can be easily found out using the SVD of this matrix T defined using the correlation matrices of the stimulus and responses. And multi-way canonical correlation analysis is a generalized version of CCA, which can be extended to more than two signals. Here, let's say we have n signals, which can be each signal can be response from a subject for the same stimulus. So if let us say n subjects are provided with a common stimulus and their EEG responses are collected and represented as x1 to xn. Now we want to transform all of them onto a common subspace such that they are highly correlated among each other. Now this is done using multi-way CCA, and since this is also a linear transform, we can represent them using matrices. This actually helps us to remove the subject-specific noise and enhance the stimuli evoked responses from each subject. In this technique, the method tries to maximize the interset correlation of the projections which is defined in this way, that is as a ratio between the between set covariance and within set covariance of the n signals. So that is the background of the linear techniques which are prevalently used for single trial analysis. Now, if we discuss about the data sets which we are going to use, so we are going to discuss about two data sets in our discussion. One is data set where the subjects were provided with speech stimulus and their corresponding EEG recordings were recorded. In this data set, 20 subjects were provided with an English audiobook, excerpts from English audiobook. And this is an open data set, which was recorded by Liberto et al. And the EEG recordings were recorded using 120 electrodes. The music EEG dataset is a dataset where the subjects were listening to Hindi Bollywood pop songs. And this is also an open dataset where the EEG recordings were recorded using 125 electrodes. We are going to perform two types of analysis, or we have performed two types of analysis on these datasets. One is intra-subject analysis, where the stimulus response correlation analysis for each subject from these datasets is performed separately. And in inter-subject analysis, where the stimulus response correlation analysis is performed for multiple subjects by aggregating the EEG responses from multiple subjects. That is, in inter-subject analysis, we consider EEG responses from multiple subjects for the same stimuli, for a common stimulus. And we try to remove the subject-specific noise by performing inter-subject analysis. And we measure the performance of these techniques which we use for this analysis using Pearson correlation, as we have discussed earlier, and another statistical test, that is pairwise t-test. So intra-subject analysis. In intra-subject analysis, we will discuss about the deep canonical correlation analysis. This deep CCA model has been proposed recently by Andrew et al. And in a deep CCA setting, what happens is the two signals are provided to a pair of neural networks. So one neural network is provided with one signal and another neural network is provided with another signal, and both of them transform the two signals onto a common subspace, and the pair of neural networks are trained to maximize the correlation between the output. So in this case, we can see as a deep CCA as a technique where the linear transforms of linear CCA are replaced by a pair of feed-forward connection neural network. So here, the same stimulus X and response Y are projected onto a common subspace, but here just the difference is a pair of neural network is used, and that is and the parameters are optimized using the stochastic gradient descent backpropagation algorithm, such that the correlation between the projected representations is maximum. So Andrew et al. Have shown that deep CCA outperforms linear CCA on image dataset with very low noise condition. But we know that EEG is a very noisy signal. So what our first set of experiments consisted of comparing the CCA performances of a linear and deep CCA on signals with increasing the amount of noise in the two signals. And as we can see in the graph here, that deep CCA does not have the upper hand on linear CCA as the SNR went less than minus 15 dB. So as noise increases, the correlation drops significantly, and deep CCA cannot outperform linear CCA. This is exactly where our EEG signals exist. So to alleviate this problem, we incorporated various levels of dropouts, and that actually helped to improve the performance of deep CCA. So for intra-subject analysis, the existing prevalent methods are three LCCA methods which were proposed by Sherman et al. And we have proposed three deep CCA methods which are homologous to the three LCCA methods, and we have shown that our methods outperform them. So basically, in these three LCC or deep CCA methods, what happens is the audio and the EEG go through a sequence of spatio-temporal processing to obtain some representations which are provided to the CCA blocks. This F1 and F2 are the CCA blocks, which are linear CCA for the three linear CCA methods, and deep CCA, that is pair of neural networks, for the three DCCA methods. And these two parameters, that is these two transforms, that is F1 and F2, are optimized to increase the correlation between the final representations from each side. So here on the speech EEG dataset, we can see that on a set of 8 subjects, for 6 subjects, the deep CCA performed better than the linear CCA. So here LCCA3 and DCCA3 are a set of homologous DCCA methods, where, as we have discussed. So and the stars represent the amount of statistical significance as a result of the pairwise t-test. So here we can see that for two subjects, the improvements were not significant, but for all the remaining subjects, for 6 subjects, it was statistically significant, and on average also, deep CCA performed better than linear CCA for the speech EEG dataset. And for the music EEG dataset, for the set of all the 48 subjects, and here is the average for all the 48 subjects, here also we can see that deep CCA clearly outperforms linear CCA. Now, another set of experiments were done where we tried to analyze the effect of deep CCA architecture on the performance of the DCCA methods. So here we can see that. So here the x-axis is DCCA models with the first as the units per layer and the second as the number of layers in the model. And here we can see that for each number of units, that is like either in hundreds or thousands, as the number of layers increase, that is the depth of the neural network increased, the performance decreased drastically. This is because of the neural networks getting overfit to the significant noise present in EEG. So now if we move on to inter-subject analysis, so let us say we have a stimulus which is provided to n subjects and their EEG recordings are recorded. A linear MCCA, as we have discussed earlier, tries to obtain an optimal linear transform for each of the EEG responses and the stimulus. If we want to represent each of them, I mean all the n+1 signals, such that they are highly correlated among each other. Now the deep variant of MCCA, that is, we want the thing which we have proposed, they obtain corresponding optimal non-linear transforms using feed-forward connections. So here we can see that this is the deep multi-way CCA model, which is a generalized version of deep CCA model. And this model takes the n inputs, it can be n+1. So the n inputs are provided to the model, which contains of n autoencoded models. So here we can consider each of them as an autoencoder, and we have n such autoencoders. So the signals are provided to the encoder section of each autoencoder, which provides an output. And here, the outputs from all the encoders are concatenated and provided to each decoder of the n autodecoders. And we collect another output from each autoencoder. Now this network is trained to maximize the correlation of the encoded representations and reduce the MSE, that is mean square error, between the input and output of each autoencoder. So this is a joint loss. So we have a generalized version of deep CCA which can take n inputs and try to maximize the correlation among them, such that which is regularized using the MSE loss of each autoencoder. So here we can clearly see what I was trying to say. So for all the n inputs, the correlation objective is to find the encoders such that the correlation among the encoded representations is maximum, and a joint loss where we also try to reduce the MSE loss between the input and output of each autoencoder. This hyperparameter lambda balances this trade-off between the correlation objective and the MSE loss. And we have seen that incorporating this MSE loss helps the network to obtain better representations, that is to increase the correlation objective. And after training this network, we discard these decoders and we collect only these encoder sections for obtaining the final representations. So here we can see the comparison of LMCCA and DMCCA, where in the linear MCCA, it outputs n+1 linear transforms, each for each signal, and deep MCCA outputs n+1 non-linear transforms, that is encoder, as we have seen in our encoder section, for each signal. So now we can have the combinations of these inter and intra-subject analysis. That is, we see here the MCCA subject as MCCA analysis as a step where we try to decrease the subject-specific noise. That is, we can use this for aligning the EEG data, and then we can use intra-subject analysis for each subject separately to obtain the final correlated representations for stimulus and response. So the MCCA step acts as a denoising step for the collection of responses which were provided for same stimulus, and then for each subject we perform intra-subject analysis. And as we have performed both linear and deep analysis for both the steps, we get 4 combinations of them. And here, comparing their combinations for the speech EEG data set, we can see that so basically these are the 4 methods, and for all the 8 subjects, these are the correlation we obtain, Pearson correlation coefficient we obtain at the end of these methods. And here we can clearly see that the deep methods perform better than the linear methods, and the statistical t-test also shows that the improvements are statistically significant. So before summarizing our talk, we can talk of the applications of this talk. That is, we can studying the auditory neuroscience or improving the stimulus response correlation analysis, we can understand how the brain encodes auditory data, how we process various types of data, and it can help us to develop smart hearing aids. Like in a cocktail party, whenever we are trying to attend to a particular speaker amidst multiple sources, we can do that. A smart hearing aid can help us do that on the go, dynamically. And recently, as JBL announced, we can also have earphones which look as a normal earphones but helps impaired people. Smart devices which can be controlled by brains can also be developed using by performing more research towards this. And we can understand how the auditory nervous system is linked to other modes of data like vision, language, memory, perception, can help us to understand a holistic view of how our brain processes information. This also provides a possibility of decoding what a coma patient can be listening to, what he can be thinking. We can extend this study to animals, especially to our pet friends like dogs and cats, and in future maybe we can have conversations with them. We can develop robust brain-computer interface devices. So to summarize today's talk, we have discussed the motivation for pursuing auditory neuroscience and challenges in understanding the brain responses to naturalistic auditory stimuli. We have discussed highly prevalent linear methods like temporal response function and CCA for single trial analysis. We have discussed the proposed deep learning frameworks for audio-EEG analysis, for intra-subject and inter-subject analysis, and compare their performance with their linear counterparts. And we have seen that the deep models were outperforming linear models. So the future directions for this work can be to collect more naturalistic audio EEG data. This is the most important step, because as we have seen in here, like as we were increasing the complexity of the neural networks by increasing the number of layers, the performance was decreasing. That is, the models were getting overfed to the noise present in EEG. and this can be alleviated collecting more collecting more naturalistic audio EEG data. So that will help us to deploy more complex machine learning models. And deploying this analysis to other brain recordings data like fMRI or MEG, we can also explore more kind of nonlinear models for this analysis. And we can improve this study by understanding the learned features by the proposed deep learning models. And this concludes my talk. Thank you. And I'm available for questions.
Hello.
Yeah, what?
Yeah, I have a question. I'm not very familiar with this area, but
Yeah.
I was wondering how, say, parameters like sampling frequency or the number of samples that we process at a time, how that can impact the performance of, say, linear models and compare it with the deep learning based models. Can
Yes,
you comment on
definitely.
that?
Yeah, so as far as I know, the basically the data sets. So these data sets. So the sampling frequency which we're talking about is limited by the sampling frequency of the brain signals recording techniques like EEG. So even though, as I have said, EEG can record up to 10 kilohertz of sampling rate, but we have seen that the prevalent techniques use a sampling frequency of like 128 hertz or 512 hertz. But then again, to reduce the noise, to remove, there are some effects like detrending. To remove the effect of those noise, we subsample them to like 64 or 80 hertz. So as you said, that also limits the analysis. But it has to be done because of the significant amount of noise present in the EEG. So yeah, better temporal resolution can help us to understand auditory perception even better. Correct. Did I discuss what you were pointing at?
Yes, yes, yes. Yeah, I was also wondering how the number of samples that we process at a time uh, shows up in this. Like, say you have collected say 1,000 samples, but you might be able to like process all of them at once, or maybe only process 10 of them at a time, and like we can think of such settings, right? So would that
Yeah.
matter?
Yeah. So are you talking about like temporal information, like at this instant to the like last 1 second or last 2 seconds kind of thing,
No,
or
I'm thinking of more like you are doing it live. Like as you obtain data, you process
yeah,
it somehow
yeah,
real time. So
yeah.
you may not be able to accumulate like 1,000 or 2,000 samples. Maybe you have
Yes,
to work with a smaller block length.
yes.
The
So you're
sample
talking about
frequency may be fine,
latency,
but
right?
yeah,
Yeah.
yeah.
Yeah, so that can be can be improved only by improving the brain recording techniques like EEG. So like as far as computing, I mean like doing our modeling on the recording signals, we have better infrastructure, right? But for the bottleneck for the process which you are talking about, I think it exists at the recording phase.
Yeah, thank you.
Thank you.
Anyone else has any questions? So thank you, Jaswanth, for the interesting talk. Please accept this memento on behalf of IEEE-IISc ComSoc and signal processing chapters. We wish you all the best for your future endeavors.
Thank you, RK, and thank you, IEEE Communication Society, for giving me this opportunity. Thank you.